My name is Dr Michelle Dickinson. I've learnt that breaking things down is the easiest way to understand them. So join me. We'll break down scientific concepts, meet some amazing scientists and inventors, and help you discover the world around you.
Hi, I'm Dr Michelle Dickinson, and today we're going to be learning about materials. Usually, when people say materials, they think of soft fabrics like those used for making clothes. But more broadly, materials are actually any physical substance that things can be made from. By the end of this episode, you'll understand what types of materials there are, both natural and man-made. We're also going to become materials engineers and learn how to measure and then harness the properties of different materials to help solve some of the world's biggest problems. Of course, we're also going to be doing some experiments that will show you how fracture mechanics engineers, like me, break things, to learn more about them. To do the experiments with me, you will need a couple of squares of chocolate, put one in the fridge and leave the other one out, a couple of sandwich or bread bags, tissues, cotton wool balls, or ideally, some margarine, and something to hit them with. I've got a hammer, but you can just use a spoon. Also, don't forget your notebook and pen so that you can write down your observations. If you haven't got those things to hand, go and grab them now. A bit later in the show, I'll be checking in with one of my science helpers who'll be joining us from home and speaking to one of my friends who'll be talking to us about their research into materials. Okay, let's get started. Everything around us is made up of at least one type of material, and it will have been selected for a practical reason, thanks to materials engineers like me. For many centuries, people had to make do with materials that were easily found in nature. Things like wood, stone, and bone were used for tools, jewelry, and building. Natural fibers like silk and wool have also been used for clothing for centuries. And while we still use them today, they really aren't as common as more modern fabrics like polyester. People then discovered ways to make man-made materials. We started with ceramics, which were used for pottery for cooking. Then metals, which were used to make stronger and tougher tools. Much later on, humans invented plastics. Look at the chair that you're sitting on. What is it made out of? It probably has legs that are made from something strong, like a metal or a plastic, or even something natural like wood. While you probably don't even think about your chair very much, you just sit on it. Engineers will have spent lots of time researching how much weight it can take, how much friction it can resist, also how much temperature and UV it can tolerate, especially if it's an outdoor chair. All of these considerations look at the properties of the material, which include strength, ductility, heat, and electrical conductivity. When we look at the properties of a material, we're asking ourselves, how does that material behave under all of those different conditions? So, if you are deciding on which is the best material to use for something, then there are a few things that we need to think about first. Strength. This is the ability of a material to withstand an applied load without breaking or bending. We can measure tensile strength, which is how it resists pulling, or compressive strength, which is how it resists being squashed. Let's look at this spaghetti strand. It's quite strong in tension. I'm pulling it now, but if I try and push on it, it's very weak and it breaks. That's because it's not strong in compression. Now, toughness. This is the ability of a material to absorb energy and bend or change its shape without actually breaking. Let's take a look at this little jelly candy. This jelly candy is very tough. If you take a look at it with this hammer, you can see that it didn't break. It just squashed a little. That means it's very tough, but it's probably not very strong And when we pull it, you can see that it doesn't break in a brittle way. Instead, it stretches first. Now, breaking materials is a part of my job as a materials engineer. But we don't just break them for fun. We look closely at the pieces after they have broken. So let's take a look at our spaghetti and our candy close up. We can see that the spaghetti snapped into sharp pieces. We call this brittle failure, and this occurs in glasses and ceramics. Think of when you last saw a plate or a cup smash. If you had collected up all of the pieces, you may have been able to glue it back together to look like its original shape. Our candy, however, has become thinner and longer. If I tried to glue these two parts together, it would not look the same as it did before. This is called ductile failure. And both ductile and brittle failure can be useful, and we will look into these more in detail later on. Finally, another useful measure is conductivity, which is the ability of a material to pass heat or an electrical charge. Sometimes we want the heat to pass through quickly, like the element of a stove, but other times we want it to go very slowly. For example, my coffee mug. I want the heat to stay in the cup rather than pass through, otherwise I'd burn my hands and my coffee would go cold very quickly. Scientists are still discovering and creating new materials to try and improve what we already have. Many new materials have come from mixing two or more different materials together, or by changing the way that we process these materials so that they can give us different properties. For example, different metals can be mixed together to form new alloys, or metals and ceramics can be mixed to form what's called a composite. These mixtures in the right combination can help us to get the exact properties that we need for a task. When it comes to testing the properties of materials, I've got a couple of experiments to help us think about how we can measure them. Let's give my science helper a call to give us a hand. Hey Rakei, how are you?
I'm good.
Thank you so much for helping with science today. Do you have the ingredients that we need? So do you have 2 chocolate bars, one that's cold in the freezer and one that is warm?
Mm-hmm.
And then do you have 2 sandwich bags, some icy water, and some butter, margarine, or some cotton wool?
I do.
Perfect. The first thing we're going to talk about is how materials break. Have you ever seen a chair before?
Yes, I have.
What do you do with a chair?
You sit on it.
Now, what is your chair made out of?
It's made out of wood?
Have you ever seen a chair that's made out of chocolate?
No, never once in my life.
Do you think chocolate would be a good thing to make a chair out of?
No.
Why not?
Well, because it would melt.
Very good, because it would melt. And so this is where we're talking about the heat properties of a material. And we're going to test that today. So I want you to take your 2 bits of chocolate. You should have one that is warm and one that is cold. And do you have something that you can hit them with or break them with?
I have a hammer.
A hammer is good. So we're going to go to our cold one first. Take your hammer and I want you to smash your cold one for me and see how it looks. Go. Perfect. Okay, I'm going to smash mine. And can you see, if you look at the pieces of the cold one, they broke into very, very small pieces, but they're actually quite harsh in how they broke. It almost shattered. Can you see how it shattered?
Yes.
Now, I want you to hit the warm one. Do you think the warm one's going to be different or the same?
I think it's going to be different.
All right, give it a hit and let's see what happens.
It didn't really snap.
It didn't snap. That's right, mine didn't snap either. You should see that the warm one just squishes a little bit, but it didn't break in the same way. Is that right?
Yeah, that's actually true.
And this is actually what happens to materials when they get cold. They become either brittle, which means they smash, or they just bend a little bit. Now, this was really important. Have you heard of a boat called the Titanic?
Yes, I have.
And do you know what happened to the Titanic?
It sank?
It sank. And the reason why it sank is because the metal it was made out of was in very cold water when it hit an iceberg. So take a look at your chocolate. Do you think that helps you explain the Titanic? If the metal is very cold, like the very cold chocolate, and it's hit, what happens to it?
It, breaks?
Very good. Whereas if the metal had been warmer, if it had hit the iceberg, it may have just bent or squashed a little bit and therefore wouldn't have sank. And so this is a really important lesson in how materials need to be tested at all temperatures before we build things out of them.
Can I eat it?
Yes, just a little bit, because we've got another experiment to come. Okay, so our next experiment is going to be talking about how materials behave around heat or electricity. We call that their conductivity. And so what we're going to do is we're going to put your hand into a sandwich bag. And then stick your finger out like this, so you've got one finger sticking out of the bag. Very good. Now I want you to coat your finger into something that we think is a good insulator. So do you have some butter or some margarine there?
I got some butter.
Okay, spread some of that butter over your finger in the bag. How does it feel?
It feels weird.
And then when you finish doing that, put that hand with the butter on it inside another clean sandwich bag. Cool. And squish the butter around your finger to make sure that your butter is totally covering all of your finger. All right, now bring your bowl of icy cold water in front of you. So there are some animals that, like walruses and seals, that live in really cold places, and they are surrounded by a layer of blubber underneath their skin. And blubber is just fat. And what we have done is make some blubber for our finger. We've put some fat around our finger. And we're going to see if this helps to keep us warm in very cold waters. So here's what I want you to do. Take your uncovered finger and put it into the icy water. How does it feel?
It feels cold.
Keep it there. Now take your covered finger and put it into the water. How does it feel?
It feels warm. It just feels the same.
It feels exactly the same. And that's because the butter is creating a layer of insulation, because it actually doesn't conduct heat very well. And there you go. That is how you are able to stay in cold water for a very long time. You can take your fingers out now before they get too cold.
Yeah.
And so insulating materials we use for everything. Your curtains in your house will help to keep your house warm through insulation. And you may have insulation in your roof in your house to keep the heat in. And it works on the same principle. It doesn't make the heat transfer very easily, so it can stay where it needs to stay.
That is actually quite interesting that I can really put my finger in and it won't hurt. I can win any contest with that.
You can totally win a contest with it. Rakei, thank you so much for helping me today. I'll see you next time.
Bye.
Okay, after any experiment, we need to write down our observations. These help us to understand our results and make interesting predictions for our next experiments. So, our observations. What did we see? The cold chocolate shattered when it was subjected to impact. This made it brittle. The warm chocolate, however, squished a little bit into a different shape. This is what we call ductile. Have a think about when you might want something to fail in a brittle or a ductile way. What about your car? If your car were to crash, would you like it to shatter in a brittle way, or just bend and absorb the energy in a ductile way? This is how we have to think as materials engineers. Now let's move on to the conductivity experiment. We found that the margarine didn't transfer heat very well, which kept our finger warm in the icy water. That meant that the margarine was an insulator. By asking questions about why something happened or how we might make it happen again, we're really starting to understand the science behind it. For example, we know what happened with the chocolate. But what about a different material, like maybe a marshmallow? Would it behave the same? Do you think that the size of the material would make a difference to how it breaks? So we saw that the margarine helped us with insulation against cold. But do you think it would do the same thing against something very hot? Okay, now we have a little bit more understanding around what materials are. We're going to talk to somebody who works on discovering new materials and why they do it. Dr. Nicola Gaston is an Associate Professor of Physics and co-director of the MacDiarmid Institute. She spends a lot of time thinking about atoms and how to create amazing new materials that most of us can't even imagine. Hi Nicola, how are you?
Hi Michelle, I'm really well.
Thanks for joining us today. Can you just explain what your job is?
Well, I work at the university, which means I do a lot of teaching. So I teach people physics and also materials science and the physics related to materials. And so the other part of my job is to do research. And that means asking questions about how materials work and trying to figure out ways of making materials work the way I want them to.
And so what is the coolest thing about your job?
Getting to have crazy ideas and then test them. So things that sound a bit more like something you'd read in a science fiction novel and see if you can make it possible and see if you can make it work.
Can you sum up your research in one sentence?
That I try to understand how atoms behave and persuade them to do what I want them to in order to have a material with a particular purpose or a particular application.
And if I'm a student now and I'm thinking about what I want to do in the future, what would you say to a student maybe about what you're doing and how it might relate to the world?
Well, I think it's really interesting that people have talked about energy sustainability for quite a while, and we know about climate change and that we still need to have energy from somewhere if we're not using fossil fuels. And so we want solar energy, for example, and we want to be able to use that in a sustainable way that isn't polluting. But with materials, it's kind of even more true, because energy from the sun, that keeps arriving on Earth. Every day there's more energy coming in, right? But the atoms, the elements that we've got on the planet, they're all here already, and we're not getting any more of any of them. So once we use something and we put it in an iPhone, and then we say we can't recycle that iPhone, it just has to go and sit somewhere, then we've locked away a whole lot of elements, like specific types of atoms that are really useful for particular things. And so we have to figure out how to do better. We have to figure out how to recycle, how to reuse individual atoms almost. It's a thing that I didn't really think about until a few years ago, but I think it's becoming really, really important. And material science is the way that we're going to be able to solve those problems.
So do you have a lab? What does it consist of?
My lab is probably my office. It's a computer on a desk and a place I meet people, and it's got lots of books in it. And that's probably the first place I go when I'm trying to think of a new idea and trying to think of, well, if I want to make a better solar cell, for example, firstly, you want to know what other people have done already, and so we tend to Google and look online and see what's already out there. But secondly, you want to sort of understand the basic physics and chemistry, and you want to have ideas about how to do things that other people haven't already done.
And before you go, do you have one awesome fact that you would like to share with us?
Gold's maybe a good one, because gold is, well, it's obviously worth quite a lot, and it's pretty. And as a physicist, I think one of the really interesting things is that gold is only yellow because of relativity. So Einstein's theory of relativity. If the world wasn't relativistic, then gold would actually be silver. It wouldn't have a nice yellow colour to it at all.
That's fascinating. And actually, if you're at home, why don't you look up gold and what colours it is at different size scales too? Thank you so much, Nicola, for beaming in to see us. It's been fascinating.
It's always lovely to talk to you, Michelle. Thanks for having me.
Okay, so we've talked a lot about what materials are and how to select them. But there's actually a whole other area that we haven't yet explored. And that's the world of biomaterials. Our bodies are amazing, but sometimes we just need a little bit of help. I'm sure you've heard of somebody maybe getting a hip replacement or a pacemaker. Whether it's because of aging or accidents, or maybe just the way that we're born, sometimes we need to help our bodies out with an artificial part. The challenge is that our bodies are actually really good at detecting materials that aren't supposed to be there and trying to get rid of them. You'll know this if you've ever had a wood splinter. Sometimes they can get trapped in your finger, and you would have seen a process called rejection in action. Firstly, your finger will start to become inflamed as blood rushes to the area, and with it brings cells from our immune system to try and attack anything attached to the splinter, like bacteria, as these could infect our body. Next, the area will swell and be really painful. This is your body starting the process of trying to push the splinter back out of your body where it came from. If you leave the area covered so the skin can stay soft, you might find that the splinter is gone within just a few days. Firstly, great job, body. But secondly, this can be a problem. Your body can't tell whether the foreign object inside it is for your own good or if it's bad. And the great news is that while it got rid of the splinter, this could be terrible news if it's trying to get rid of your brand new hip. This is where biomaterials come in. These materials are amazing because they can trick your body into thinking that they're already supposed to be part of you. They've been designed to give the same strength and ductility as the natural material that they're replacing, while also having a surface chemistry that the body will accept and doesn't try to get rid of or reject. While some materials naturally don't cause a rejection reaction by the body, others may need a special type of coating so that the body can't detect the underlying material. Biomaterials also have to be non-toxic so that they don't cause us any harm once they're inside our body. Biomaterials that work well in the body are called biocompatible, and these include metals like titanium and stainless steel, as well as medical-grade plastics like PVC and polyethylene. If you watch any science fiction movie, you might see some examples of how we could adopt biomaterials to enhance our natural abilities. Think superhuman strength or implanting computer technology inside our brains. While ethically speaking, this might not be a great idea, scientifically speaking, this could actually happen. Materials make up the world around us, and hopefully, as new materials engineers, you might start to look differently at the things around you too. Ask yourself, I wonder why they chose to make this out of that. Test your theories and don't be afraid to try and break some things every now and again too, just to see if you're right. We rely on the strength of materials to keep our buildings standing, planes in the air, and even just to make sure that your tablet doesn't break when it hits the floor because you've dropped it. New materials are being invented all the time to help to solve problems that we have across the world, and there's so much more to discover. Teachers and parents, don't forget to visit nanogirlslab.com, where we have downloadable content to help you continue on your science journey of materials. Thanks for watching. Why do we need insulation, both for our homes and for our bodies? What do you think the worst material would be to make a car from, and why? Which materials are safe to go inside our bodies, and which do you think we should steer clear of?